butene and made a load of isomers with Molymod. So we made but-1ene, but-2ene, and we looked at the cis-trans isomers of but-2ene. Those cis and trans isomers we mentioned in a previous lesson, but we're going to look at them in detail when we do high-level organic chemistry. So don't worry too much about that. Just wanted people to have a go with the Molymods and make isomers. We made a load of other isomers of butene as well, like cyclobutane and methyl cyclobutane and others. We might have a look at halogenoalkanes again. I think at the end of last lesson we looked at what we mean by primary, secondary and tertiary halogenoalkanes. When I did this with the other group, quite a number of people unsurprisingly had forgotten what we meant by primary, secondary and tertiary, so I reminded them and I'm going to remind you now. And it's my chance to remind you that I'm not going to give you all that much homework in this topic, partly because you've got loads of stuff going on like EEs and whatnot, but you're also working hard on high-level bonding and a test for that, and you've just done a test for me. So I'm going to try to minimise homework, and I'm probably not going to do a test for standard level bonding. It might be that I just roll it into high level, do it all in one go next year to save a bit of time. Right, but anyway, last time we looked at a tertiary halogenoalkane, a secondary and a primary. What we learnt last time is that a tertiary halogenoalkane is called a tertiary halogenoalkane because the carbon that the chlorine is attached to 1, 2, 3 carbons, hence tertiary. Remember doing that last time? And this is the same molecule 3 times drawn in 3 different ways. Okay, just reminding people about the displayed formula, the skeletal formula, and the condensed structural formula. So we're just practicing those. And practicing naming as well. So this is 2-chloro, 2-methylpropane. So just remind you that naming, you find the longest carbon chain, propane, and then you put the side chains in front of it. So it's 2-chloro, it's on the second carbon, and the numbering of the chain is 1, 2, 3, and it's got a methyl group on the second carbon. Right, so 2-chloro and then 2-methylpropane. So if you want to there's literally no point making a note of that because you have got that in your notes from last time. What we did have time to practice is primary and secondary with the other group, but I'm not going to do that because we're going to look at alcohol. So this is where you're going to start making some notes for today, please. So alcohols is a family of molecules you need to know about, a homologous series, therefore, and it contains what we call the hydroxyl or hydroxyl functional group, which is OH, but that OH has got a line coming from it to join to a carbon. And I've given there an example of a primary halogenoalkane that you saw at GCSE, I think all of you, which is F because of 2 carbons, An because it's got no double bonds, Ol because it's an alcohol, F-an-ol. So every bit of that name relates in some way to its structure. So I'll pause the video for people to write up and you guys can copy it as well. So there you go. The secondary alcohol, I'll just show you this, and I'll just vise this way for a second. The secondary alcohol has got, we look at the carbon that's attached to the hydroxyl, and we count how many carbons that's attached to. 1, 2, which is why it's secondary. This one, the carbon that's attached to the hydroxyl has got 1 carbon on it, hence primary. The carbon that's attached to the hydroxyl has got 2 on it, so secondary, right? It's the same naming system for halogenoalkanes that we looked at last time. There's your tertiary alcohol, as you were suggesting, Arsene. If you put a methyl group, depending on where you put it, you can turn the alcohol we just looked at into a tertiary alcohol. So just to remind you again, we look at the carbons attached to the OH, and we see that there's 1, 2, 3 carbons attached to it, hence tertiary. And we learn next year that in fact we learned this year, it's in standard level, that primary, secondary and tertiary alcohols just behave a little bit differently from each other in terms of what chemistry they can do. Take the time with the skeletal picture in the top right and make sure you understand what that means and where and how that relates to the displayed and the condensed structural formulae. That's often something people struggle with. I want you to be able to do all 3 structural types. So each vertex, each end of a line is a carbon. So this is a carbon, this is a carbon, this is a carbon, this is a carbon. So that's 1, 2, that's those 4 carbons, right? With skeletal formula, we don't draw the carbons, we just have the vertices, and we also don't draw any hydrogens that are attached to carbons. We draw all other hydrogens though. So if I number these and then relate it to these, let's call that one 1, 2, 3. It doesn't really matter, it could be this one or this one. I'm just going to use this one as an example. Do this one here. 1, 2, 3. The only one that matters here is carbon 2, because carbon 2's got to be the one that's got 3 carbons coming off it and an OH. So that one we'll call carbon 4, that can be carbon 4. Notice that these 3 are all exactly the same as each other. If you were to make that, in fact I might get you to do that in a sec, you'll realise that this is a very symmetrical kind of looking molecule. So once you've drawn it, why don't you have a go at making that with Molymods? So the carbon's attached to the hydroxyl there, it's got 3 carbons coming off it, so it's tertiary. Right, a little bit of basic stuff then. Alcohols have a hydroxyl functional group, which means they make hydrogen bonds on top of the dipole-dipole and London forces. And compared to molecules of similar size, which is probably a little detail you should add, they have relatively high boiling points. So if you compared, say, methanol with ethane, roughly similar molecular mass, ethane is very much a gas at room temperature, and methanol is a boiling point of in the tens of degrees C. Okay, so the hydrogen bonding there is to remind you that there's so much of organic chemistry links to bonding, intermolecular forces, shapes of molecules, all of that stuff. It's worth, if you need to, particularly over summer, refreshing your memory and all that kind of stuff. That's good. I'm going to briefly spend some time on what we call ethers. Now, before you start copying, can I just walk you through it and then you can copy? Is that all right? So, because of I'm using notes from the other lesson, it's all on the page already. The ethers are an isomer of alcohols, right? So, if you imagine ethanol has got 2 carbons, 6 hydrogens, and 1 oxygen. This has also got the same number of carbons, hydrogens, and oxygen. So, it's an isomer of an alcohol, but it hasn't got an OH, it hasn't got a hydroxyl. Instead, it's got what we call an alkoxy group. So let's add that detail. It's it's not a sheet that I'm going to give you anyway, but it's got an alkoxy functional group in it. Right? And so the naming of ethers, you don't need to worry about. I've given you the names, but for your course, you don't need to know the names. Although I am going to triple check that before I let you run loose a bit. So you've got an oxygen in the middle of the molecule, in this case with a methyl group either side. We call that methoxy methane. Methoxy methane. Or here's another ether, just an oxygen in the middle of the chain. This time it's methoxy ethane. Or you can even have a more complicated looking ether like the one at the bottom. This would be methoxy methoxy propane, but because it's on the second carbon of the propane, 1, 2, 3, we call it 2-methoxy propane. So there's 3 examples of ethers. All you need to know, well, it's weird that they ask you to learn this at IB really, because you not really do much about ethers at all. I just want you to know what they are. All you need to know really is that you've got oxygen in the middle of a carbon chain. That's all you need to know. And there's just a few different examples of them. Probably worth getting into the habit of always drawing lone pairs on oxygen, so you remember that it's got that bond angle, the same as water, of 104.5, which is why it's drawn like this. So get into the habit of drawing lone pairs on oxygens, because they're always there. Right. Ethers, that was that. Spend a bit of time now on amines. So I'm in a phase of just introducing you to a whole load of different functional groups, right? And we're going to use them and learn about them. When you're drawing these, before you write, just let me blabber for a bit, and then you can process what I'm saying. But I want to point out to you that amines are a homologous series that contain what we call the amino functional group. The amino functional group is basically just a nitrogen, and that nitrogen's either attached to hydrogen or carbon, nothing else. Right? And nitrogens will always have a lone pair. Oxygens have 2 lone pairs, nitrogens have 1 lone pair. It's good practice to get into the habit of drawing a lone pair on them, so that when you're drawing Lewis structures with nitrogens, There are exceptions, like nitro groups don't have them. Nitrates don't have them, for example. But in organic molecules, amines will have lone pairs like this, and that's what determines their chemistry. So partly it affects the fact that they can make hydrogen bonds, just like alcohols can, so they can make H bonds. And the chemistry that we'll learn about amines, their basicity and their nucleophilicity, phrases that we'll learn in time, relates to the fact they've got a lone pair on there as well. Right? So amines are a bit like alcohols, but they've got an NH2 instead of the OH. But this is what we call a primary amine, where the nitrogen is attached to one carbon. Notice the primary, secondary, tertiary numbering rules are different to halogenoalkanes and alcohols. Here it just count the number of carbons on the nitrogen. So we've got ethyl amine, where we've just got an ethyl group, 2 carbon chain hanging off the amine. We've got a secondary amine where we've got 2 carbons, 1, 2 coming off the nitrogen. Again, lone pair. Nitrogen's making 3 bonds as always. We call that one dimethyl amine. Di, because there's 2 of them, methyl 1, 2 amine. And a tertiary amine, which has got 3 groups coming off the carbon. Beg your pardon. 3 groups, 3 carbons coming off the nitrogen. 1, 2, 3. So that's tri, because there's 3 of them. Methyl, because they're methyls. Amine, trimethylamine. Okay, and you can draw it like that skeletally. You can draw it like that, or you can even draw it like that, which would be a version of the condensed structural formula. Okay, and again, there's some similarities and differences between how the different amines behave that we'll talk about a tiny bit in other times. But for now, you just need to know what primary, secondary, and tertiary amines are and how to draw them. So if you just get on with that for a bit. So we're going to learn about another functional group which is found in 2 different homologous series, which is kind of confusing if you think about it, because you're used to an alkene being only in alkenes, or an alkoxy only being in ethers, or an hydroxyl only being in alcohols. A carbonyl, which is a C double bonded to an oxygen, it has to be a double bond, is found both in aldehydes on the left here and in ketones. So aldehyde is a homologous series that has got a carbonyl, and a ketone is a homologous series that's got a carbonyl. There's a subtle difference between the way that the carbonyl is used in an aldehyde and a ketone. The only difference between them, really, they behave very similarly, by the way. An aldehyde is when you've got the carbonyl, which is this, at the end of a carbon chain. In other words, it must have a hydrogen attached to it. So an aldehyde has got a hydrogen attached to the C double bond O. So it's a carbonyl with an H on it. It's an aldehyde homologous series. And aldehydes, we give them the name eth because of 2 carbons, and because there's no carbon double bonds, al because it's an aldehyde. Again, the naming rules are really similar. Very similar to ethanol, which is OH, remember. So this is ethanal. The way that we draw that in the condensed form is like this. So the CH3 is like before, but here, this CHO is something that we have to learn, is the way that we write aldehydes in the condensed structural formula. So if you ever see CHO, it's always an aldehyde. So it's CHO, that's what the CHO is there. So that's ethanal. We just talk about the ketones for a minute. Here, we've got a carbonyl again, but this time it's within the carbon chain. So it's on a carbon that hasn't got hydrogens attached to it. It's got a carbon either side, in other words. So it's part of that bit's the same as that bit. The only difference is this one's attached to an H, this one's attached to 2 carbons. Again, the naming rules are quite straightforward. And you only need to recognise very simple ones, like this one here, which is propanone. Prop because it's got 3 carbons in the chain, and because there's no double carbon bonds, carbon-carbon double bonds, and one because it's a ketone. Right, so propanone. This is otherwise known as acetone, which many of you will know the smell of, because it's the stuff that you get nail varnish off with. It's nail varnish remover. That's what that chemical is, that stuff. And these are molecules which will look at the properties of them, but basically the properties boil down to the intermolecular forces they can make. So can they make hydrogen bonds with themselves? Yes or no? Can they make hydrogen bonds with themselves? Very firm nod there from one of the people in the room. Can you explain why it can make hydrogen bonds with itself?
Because there is a oxygen and it has two lone pairs, so therefore it can act as a hydrogen donor.
Hydrogen bond acceptors, yeah, it's got hydrogen bond acceptors, and if we're drawing oxygens, remember I told you to draw lone pairs on them, so we've got lovely hydrogen bond acceptors there, very nice, so it can make hydrogen bonds. But what else do you need for a hydrogen bond?
You need the hydrogen directly attached to either oxygen or nitrogen or fluorine.
And is there a hydrogen attached to oxygen, nitrogen or fluorine in either of those two molecules? So can they make hydrogen bonds with themselves? No, they can't. So you know the answer, you just jump to the answer thinking it through, all right? So, and that's normal. They can make hydrogen bonds with other things, so both of them, particularly propanone is really quite soluble in water, and I think ethanol is as well, actually, because it can make hydrogen bonds with water through the lone pairs you just described there, okay? So, two families to know about then, aldehydes and ketones. I'll make a few notes. By the way, with ketones, I say it looks a little bit, it looks to me a little bit like a lock. You know, you kind of get this shape for a lock. If you draw a sort of simplified lock, it would look something like that, right? You know what I mean? A keyhole, if you like. I think that looks like a keyhole, and ketone looks to me a little bit like a key. Looks a little bit like that, right? So keyhole, ketone. Stupid ways of remembering things. This is how. I mean, I've obviously been doing this a while now, so I just kind of know it now. But when I learned them when I was in year 12, like you guys, that's what I aldehyde and ketone looks like a keyhole, right? Get those down. And notice, by the way, the condensed structural formula is CO for a ketone in the middle there. I'll draw the condensed, no, what do you call it, the skeletal as well, which are like that. Notice we don't draw that hydrogen on the aldehyde because it's a hydrogen attached to a carbon. Okay. Just for the sake of the people not here, I'm going to give out a sheet with all the functional groups you need to know, which I photocopied from the book. So I'll give that out today. Make sure if you're not here, you do pick one of those up. That's it for new stuff today.